Hello, my name is Yang Li. I'm the AP teacher here. Okay, so we're going to continue to talk about a very important concepts between the derivatives and the continuity. Okay, and this one sometimes students feel confused. Generally, we say derivatives means what? The graph with what? Smooth curve. Okay, no corner points. Generally, we select this one, smooth point, means they have what? Tangent line there, right? So we saw this function normally derivatives. And then continuous, what do we say? When we say continuous, means what? Means the function no hole. Of course, no hole may be smooth, but no hole may be like this. The arrow point there, corner there. So at this case, even though it's continuous, but not derivative, okay? Of course, this just generally give you some like a concept about the relationship between the continuity and the derivatives. We can say that if a function's derivatives guarantee is continuous, but if it's continuous, we don't know. Maybe derivative, maybe differentiable, maybe not. All right. So let's see the more detailed explanation about this. I just use the graph, give you the brief first. Here, like this one here. This is if a function, that function fx, right, is and a is in the domain, and then if fx is differentiable at a, then f is a continuous at a. We can prove this one very easily. We use the definition of the derivative of the function at x equals a. We will get what? We will get this, right? This one, right? That's easy. And then remember, if we want to show the functions continue, we need to do what? Limit x approach to a, fx must be equals to fa. That's the definition for continuous. All right. So we do this way here based on this one. This is limits of the function. You can change, you can minus fa plus fa. You may ask why we do that, right? Because they try to make this part. Okay. This part here, you have fx minus fa. So you have this part. And then they go this part divided by something x minus a times by x minus a. Because they time the numerator and denominator by the same number, no change of the value of the function, right? No change with the limits, right? So, and then what they're going to do, they have this one as what? This. So that's why they have limits of this and time by the limits of that. This is the property of the limits. Limits, you have the limits of the products. You can do the limits of each factors and multiply them. And the same thing with the addition. So you got this one. And now, because x approach to a, this one will be 0. So that's why here you got 0. 0 times f derivative is still 0. So that's why equals fa. You see, this one equals this one shows that this function is, if it's derivative, means it is continuous. And they use the derivative definition here, okay? So we prove now, we say that if the function is differentiable, guarantee the function is what? Continuous, right? Now, we go converse right now, okay? If the function is continuous, can we guarantee is the derivative differentiation available? The answer is no. We can pick up this example here. We can say fx equals absolute value of the x. So derivative, use the definition fx minus f0. I'm checking with what? X equals 0 there, right? Now, plug in fx as the absolute value of the x minus absolute value of 0, x minus 0. I got this now here. Be careful. Absolute value of x, I want to break down this one here to get y, you have this, okay? Absolute value of function equals what? Either equals x, 1x greater than 0. For example, you have 2 there, absolute value still equals 2, right? Equals itself. But if x is less than 0, what happens? Less than 0, for example, you have a negative 2 absolute value, still equals positive 2. But here's the x. We want to use whatever the value here to represent the answer of the absolute value. We do what? We do absolute value of the negative 2 like this. Equals what? Equals negative 2, like this. You see here? Negative and negative is positive 2, right? Still positive 2. But you got to use the original number. So that's why here you can write it as negative x. So when x approaches 0 from left side, this one will be equals what? This one will be equals negative x over x. And cancel, you have negative 1. And if you use the right side, because x is positive, that's just x over x. Cancel, you got positive 1. You see here, left limits, right limits, they're not the same. Means what? Derivative at this point, not defined, right? So that means even though the function is continuous, but the derivative at x equals 0 is not exist. It's not differentiable. The reason for that is this. When you graph it, you can see that this is a graph of fx. And you see here on this side is a positive slope. On this side is what? It's negative slope here. See that? So left limits, right, left derivative and the right derivatives, they're not same. So that means derivative at the x equals 0 not defined. Okay, this is one of the thing we can do. The other one is similar. They pick up the fx equals cube root of the x. Still use the definition, simplify, you got this one. Now, here. Because when x, no matter from left side approaches 0 or right side approaches 0, this one, the bottom one, x squared always 0. And square root 0 still 0. Or cube root 0 still 0. One over 0 is positive infinity. What does that mean? It means derivative is not defined. That's the time the graph has what? There is like a vertical line here. You see that? So that's why it's not defined. But even though the function at this x equals 0 is what? Continuous. Why continuous? Because no hole, right? Here, no hole, huh? Right? That's continuous. We know that. Or you can go like this here. You can go definition, limits, x approaches 0 from left side, right? Cube root of x still equals 0. And this one same as limits, x approaches 0 from the right side, cube root x still equals 0, right? And f0 still cube root of 0 equals 0. They're equal. Limits of the function equals the value of the function, shows that function is continuous at that point, x equals 0. But differentiation is infinitive. That's not defined. All right. Now, we showed like 2 already, and then we go to the third one here. You have the piecewise function here. When x is not equal 0, x equal fx equals x times by sine 1 over x equals 0, fx equals 0. When you do derivative use definition, you will get this, right? And then you can see that derivative of x approaches 0. This kind of thing, you can see that the graph is what keeps shaking. here, like this one, shaking up and down, like this one here. Because here, imagine if x approach to 0 from negative side, from left side, means x is negative. 1 over negative is negative. Sign negative will be negative. But if you go x approach to 0 from right side, x is positive, 1 over x is positive. Positive sign positive is still positive. So it means the left limits, right limits not equal. Means what? This one is not exist. Okay, why not exist? We can look at the graph here. This is our original function. This is this function here. This one is this function x sine 1 over x, like that. So you can see that this function is what keeps shaking up and down. So that's why they do not have derivative at x equals 0. Okay. Now we move on. We go to here. We can see that summary is this: function derivative guarantee continuous, but function continuous, we don't know if guarantee is differentiable or not. Okay. Now on the following lesson, I will explain the example 3.14 and and also the check mark questions. Okay, that's the next time. And today, this lesson, we just stopped it here. Okay, so remember the conclusion there is function differentiable guarantee continuous, means smooth curve, as what I mentioned, should be always what? Continuous. But if it's continuous, maybe there's that sharp corner point, or maybe the derivative is infinity, right? So that means not defined for the derivatives, not guaranteed, maybe, maybe not. Okay, so if you have any questions, please email me and let me know. Okay, I can help you. All right, thank you. Bye-bye.